Today's lesson is on Euler's method. And I know it doesn't look like that says Euler, but that's how you pronounce his name. So what this involves is using the slope or the differential equation to predict values near a known value. So if you know a value and you know what the tangent line looks like, for close values, you can kind of predict what the next value is going to be. Well, Euler's method kind of stacks multiple tangent lines. So we're going to go through an example using tangent lines. I'm going to show you graphically what we did, and then I'll show you another way to do the same thing. Okay, so we're going to use tangent lines. We have the differential equation dy dx equals y. Okay, simple differential equation. We have an initial condition that y of 0 equals 1. This is going to be a part of these, is what your delta x is. So how far apart are we predicting? Now, 1's a pretty big jump, but it makes the math easy. We're going to approximate the values of y of 1, y of 2, and y of 3. Okay. So starting off, we know our initial point is 0, 1. Okay, well, if that's my point and the dy dx is y, that means my slope is going to be 1. So the tangent line is going to be a slope of 1, x minus 0, and then rather than doing the minus 1 on this side, I'm just going to do a plus 1 on this side. Okay, my new x value, we're starting at 1 and I'm going up by 1, so my new x is going to be 1. My new y I'm going to get by using the tangent line. Okay, so I'll plug 1 into this equation. So we're going to have 1 times 1, which is 1, plus 1 gives me 2. Okay, if I have a slope of 1 and we're going over 1, we're going to go up 2. Or we're going to go over 1. Yeah. So that's my new point. So my new point is 1, 2. Okay, so this is my new point, which means the slope is going to be different because we've moved along the curve. So now my slope is going to be 2. And then we're going to write a tangent line with those 3. So y equals 2 x minus 1 plus our y value of 2. So my new x, we're going up another 1, is 2. And my new y is going to be, plug in 2 here. So 2 minus 1 is 1. So 2 plus 2, my new y is 4. So based on the slope at that point, we went up 2 this time. So let's do this again with the point 2, 4. So we use the new point to find the next point. Our slope is still going to be the y value, which is 4. So my tangent line is going to be 4 times x minus 2 plus 4. So if I plug in my new x, which is 3, we're going to have 3 minus 2 is 1, so we end up with 4 plus 4, which is 8. Okay, we're going to come back to this in a minute, and I'm going to show you graphically what's happening. But to understand graphically what's happening, I want to look at what this equation really is. Okay, this dy dx equals y is an equation. So if I separate the variables, dy over y equals dx. That means we have the natural log of y equals x plus c. So y is c e to the x. We have an initial condition here to solve for the c. So we know that 1 is equal to c e to the 0. So my c value is 1. So this equation is really y equals e to the x. Okay. So on e to the x, the slope at any given point is the y value. That's what e to the x is. So now what I'm going to do is graph on the calculator the exact solution, so y equals e to the x, and all 3 tangent lines. And I'm going to show you what it is we did in all of this work. Okay, so in my y equals, I have the e to the x. X plus 1 was the first tangent line, and then the other 2 tangent lines there. Okay, so I graph, and we get kind of a mess here. So we have e to the x here. We've got the first tangent line at 0, 1. So what we did is we drew that tangent line, and we actually found this point right here. Okay, then at this point we recalculated, because the slope here is going to be different. So then we recalculated and used this tangent line to get to here, and then this tangent line to get to the 3, which is up here. All right, so I'm going to clean it up a little bit by, I don't want to see the whole line. So now if I graph it, I'm just going to see the line, just part of the tangent line. So this line segment led to this point, to this point, to this point. So if I were to graph the points that we calculated in the table, this is what we would end up getting. Now, some things to note. First of all, as we moved farther and farther away from our initial point, the prediction was less accurate. But how could you make this more accurate? Well, if we did smaller deltas, this would actually be a lot closer to the actual curve. So this is what we call the numerical way to solve a differential equation. You can create the equation using the particular slopes. And a lot of computers and things like this, that's how they actually do this. So let's look at the process. Okay. You can do the tangent line approximation, and it's going to be the same process, but I kind of break it down into some simpler steps. So the first step is to start at the given xy. You will get a starting point. Okay, next we're going to calculate the slope, dy dx, at that point. Then we're going to use that to find the change in y. So the change in y dy is going to be the dy dx that we found times how big the delta is. So we had a delta of 1, so the jump was just whatever that slope was. But if our increments are smaller, if we're going over 0.1, then my rise has to correspond to that. So that's this calculation. So then we're going to create our new point. So our new point is going to be x plus whatever the delta x is, and you'll be told what that is. And our new y is y plus our calculated dy that we got from the slope. This is our new point. Then we are going to repeat this with the new point. Now you could do this many, many times, but AP is going to limit it to only 2 steps. So let's look at some more examples. So consider the differential equation given by dy dx equals xy over 4. Let y equals f of x be the particular solution to the differential equation with the initial condition f of 0 equals 2. What is the approximation for f of 1 if Euler's method is used, starting at x equals 0 with a step size of 0.5? So what I'm going to do here is create a chart to organize all the steps of this process. So I have this chart here. So what are all these categories? I'm going to have my x here, my y here, and you could just include that as one column as a coordinate. That's totally up to you. I'm going to have dy dx, and I always write the equation here. That way I know how much space I'm going to need to do the calculation. Okay, then we're going to calculate our dy, which is going to be dy dx times delta x, and that's going to give me my new x, which is x plus delta x, and my new y, which is going to be y plus dy. So this process is going to do the same thing that the tangent lines were doing, just kind of broken down a little bit. Okay, so my first x and y is my initial condition 0, 2. Okay, I'm going to calculate the dy dx, which is going to be 0 times 2 over 4, which is just 0. So dy is going to be 0 times my delta x, which is 0.5, which is still 0. My new x is going to be x plus delta x, which is going to be 0.5. My new y is going to be 2 plus 0, so it's still 2. So this is saying I have a slope of 0, so I can predict the next y value to be the same. So this is my new point. Okay, and we'll go through the same process. So we're going to have 0.5 times 2 over 4. That's going to give me 1/4. Okay, so we're going to go that slope, 1/4, but we're only doing that for 1/2 of x. So we're not going to go up and over 1/4. We're going to end up going up and over 1/8 in that half x. So my new x is 1. My new y is going to be 2 plus the 1/8. So that's going to be 16/8 plus 1/8 is 17/8. So this is my solution using Euler's method. Okay, our next example. Let f be the function whose graph goes through the point 0, 1 and whose derivative is given by f prime equals 1 plus e to the 2x over 2x plus 1, and f prime is just the same as dy dx. What is the approximation for f of 1 if Euler's method is used? Again, we're going to start at 0 with a step size of 0.5. So I'm going to make my chart. Okay, so in my chart, again, we have our x, our y, dy dx, which in this case is 1 plus e to the 2x over 2x plus 1. We'll calculate dy, which is going to be dy dx times our delta x. Then we're going to have our new x and our new y. Okay, and again, there's different ways to organize this information, and you can use the tangent lines, and if you look at other people do Euler's method, you're going to see different things. The result, however, will still be the same. So I'm going to have 0, 1, and we'll plug this into our differential equation. So we're going to have 1 plus e to the 0 over 2 times 0 plus 1. Okay, so we're going to have 1 plus 1 over 1, so that's going to give me 2. Okay, but we're not going up 1 and over 2 because we're only going over a half. So my change in y is really going to be that 2 times the 0.5. So since we have a slope of 1, or slope of 2, if I go over 1/2, we'll go up 1. So my new x is going to be 0.5. My new y is going to be 1 plus 1, which is going to be 2. Okay, so my next my next slope will be 1 plus e to the 2 times 0.5 over 2 times 0.5 plus 1. So we're going to have 1 plus e to the 1, so that's going to be 1 plus e over 1 plus 1 is 2. So my dy is going to be 1 plus e over 2 times 0.5, or 1/2. So 1 plus e over 4. So my new x, we're now at 1, which is our end destination. My new y is going to be 2 plus this. Okay, so this is going to be 8 over 4 plus 1 plus e over 4. So we get 9 plus e over 4. Alright, so we're going to do another one of these. Given dy dx equals xy minus y squared and y of 2 equals 3, what is the approximation for 1? Okay, using step size of 0.5. So start with our chart. All right, so we got our x, our y, our differential equation, calculating dy, x plus dx, and dy. All right, so we are starting at the point 2, 3, but our end destination is 1. So thinking about the x values, we're going to be at 2, then we're going to go down. So we're going to go to 1.5, then to 1. So our delta x is actually negative 0.5 because we're going down, we're going backwards. Okay, so my first slope here is 2 times 3 minus 3 squared. So 6 minus 9 is -3. My dy dx is going to be what we just found, -3 times our delta, which is -0.5. So negative times negative is 1, positive 1.5. So my new delta x going backwards is going to be 1.5. My new y is going to be 3 plus that 1.5, or 4.5. Okay, I'm actually going to write these as fractions. It's going to make this calculation a little easier. So this is going to be 3 halves. This is going to be 9 halves. So here we're going to have 3 over 2 times 9 over 2 minus 9 over 2 squared. Okay, which you can do all this math. I'm just going to jump to, it is -27 over 2 when you subtract and reduce it. Okay, so our dy -27 over 2 times a -1/2 is going to be -27/4, sorry, positive 27/4. So we finally get to our destination of 1. My new y is going to be 9 halves plus 27/4, which is, if you do the math, 45/4. Okay, our last problem here, we are not given an equation, but we're still going to use Euler's method using a chart. So the table at the right gives selected values for the derivative of a function g on the interval from -1 to 2. If g of -1 is 2, an Euler's method with a step size of 1.5 is used to approximate g of 2, what is the resulting approximation? Alright, so we're going to have x and y. My dy dx is going to be g prime of x in this case. Then we'll do our dy, and we'll get our new x and our new y. All right, so our starting y is, or -1, -2. So the slope we're looking for is the slope at -1. Well, in the chart, that gives me 2. So we're going to have 2 times my delta is 1.5. So my new x, we're starting at -1, going up 1.5. So we're going to be at 0.5. My new y, sorry, I didn't actually calculate this. 3 is going to be -2 plus 3, which gives me 1. So we're at 0.5, 1. My slope at 0.5 from the chart is 1. So we're going to have 1 times 1.5, which is 1.5. So my new x, 0.5 plus 1.5 is 2, which is our goal. My new y is going to be 1 plus 1.5, which is 2.5. So Euler's method is pretty easy, as long as you stay organized and you remember what the steps are.